Once we've established that the velocity is fully developed, this implies that du dx is equal to 0. In general, you would expect that u would be a function of x and r. So, if du dx is equal to 0 in the fully developed regime, it means that u is not a function of x and is only a function of r. So the velocity field is only a function of the radial coordinate. And again, this is the case where this is fully developed. At that point, it's useful to consider how mass conservation or continuity impacts our understanding of the problem. So continuity is oftentimes used interchangeably with the mass conservation equation. And here we're looking at a cylindrical symmetric system, so dd theta is equal to 0. Well, if du dx is actually equal to 0 because we're fully developed, the implication from the perspective of the mass conservation or continuity equation is that 1 over r ddr of rv is equal to 0. So let's make sure we're notationally we understand what we're saying here. U is the axial velocity, or the velocity in the x direction. V is the radial velocity, or the velocity in the r direction. So, if we have that 1 over r ddr of rv is equal to 0, we multiply both sides by r, and we have ddr of rv is equal to 0. We integrate it once, and we have rv is equal to a constant. So this is after one integration. We don't know what that constant is, but we have a way of identifying it, and the way we do that is we say, well, is there somewhere where we know what v is? And we go to the wall. So if this is the center line, here we're calling the wall the location r0. So v at r is equal to r0 is equal to 0. Well, because it has to be constant throughout, it means that v of r is equal to 0. So this is an important finding. It says that for fully developed flow, and again, this is hydrodynamically fully developed as compared to thermally fully developed. So we're only interested in the momentum equation at this point. The radial velocity is 0, and this is in an impermeable, non-porous. This is in a wall where there's no transpiration. So what we'd like to do now is we'd like to use some of this information to understand better what the implications are for momentum conservation. So imagine again that we have this tube, and what we're looking at here is we're looking at a small control volume, and sometimes it's easier for me to think about this as we're actually looking at, so if we have this three-dimensional system, what we're looking at is a slice in there where that slice has a thickness delta x and a thickness in this direction delta r. So it's it's almost like we're looking at a little wheel or a little circular section in there. And for that little control volume, we're going to apply a force balance on it. So the force balance on this guy says that we have to think about what the forces are. Well, there's a pressure force that's acting on it. This is a normal force, so it acts on the face of it. And there's a shear, or there are shear forces happening or acting on it. And so as we look at this little element there, it's pretty clear we need to think about what the area of action is. So pressure, of course, has units of force per unit area, Newton per meter squared. And the shear, tau, minus mu du dr also has units of Newton per meter squared. So in both cases, there has to be some appropriate area that we're acting on. To be clear, this 2 pi r delta r, remember what we said, we're really focusing on this geometry shown here. And so the pressure's acting on this face that I'm coloring in right now. If you think about what that area is, if this were really a cylinder, it'd be 2 pi r, which is the perimeter, times the thickness, delta r. So again, remember, delta r is that. So 2 pi r delta r is that area. On the sides where the shear is acting, the area is 2 pi r times delta x, because again we noticed that we noted that this dimension is delta x. So when we have this as the force balance on this system, we're saying that the pressure forces balance the viscous forces. The viscous forces are these shear forces. And we simply pose the problem as the forces in one direction are balancing the forces in the other direction. And so we have forces that are acting on the x face, forces that are acting on the x plus delta x face, forces that are acting at the r location, and forces that are acting on the r plus delta r location. So we have our x and r location, and we have our x plus delta x and r plus delta r location. Well, we use the definition of a derivative or do a Taylor expansion. There are different ways of thinking about this. All we're really doing is we're asking the question, what is x, what is, for example, 2 pi r delta r p x minus 2 pi r delta r p x plus delta x. So we pull these guys over here. We pull our shear terms to this side. We divide by 2 pi r delta x. And then we do a limiting process. So this limiting process is using the definition of a derivative. And in doing so, we get this differential equation in terms of the velocity gradient or velocity derivative with respect to r and a pressure gradient in x. Now, one of the things that we talked about in the fully developed case is that u is only a function of r and its derivatives and dp dx. So one of the implications there is that, and we'll talk about this perhaps a little shortly, is that if u is only a function of r and p is a function of x, these things must be equal to a constant. So really we take the r over to the other side to make this clearer. For all differential equations, so this is a second order differential equation. There are boundary conditions, and so there are two boundary conditions for this problem. R is equal to 0, a symmetry condition which says the velocity field is symmetric, du dr is equal to 0, and u is equal to 0 on the wall. So that's our no slip condition. Because dp dx is, because both of these terms are equal to a constant, so dp dx is a constant, and the reason we said that this is true is that we had this function of r equaling this function of x, and this means that they're both equal to some constant. We can integrate dp dx with respect to r, and that's how we get this. We integrate our the r on that side, and we get r squared over 2, and a constant of integration. We divide through by r mu. Because du dr at r is equal to 0 is equal to 0, our symmetry condition, C1 is 0. We integrate this again, and we get r squared over 4 mu dp dx plus C2. We apply our no-slip boundary condition, our second boundary condition. We're calling this u of r is equal to capital R is equal to 0. So take a look at that. 0 is equal to capital R squared over 4 mu dp dx plus C2. So we get an expression for C2. And we substitute that into our original u of r equation, and we get that well-known parabolic velocity profile for u of r. So u of r is parabolic. And the centerline velocity is the maximum value. Its magnitude is this r squared over 4 mu minus dp dx. Sometimes we talk about something called the bulk velocity, and it's this area-weighted average velocity. So we're integrating, so what we're saying in sort of a more meaningful way of thinking about it is, if I wanted to talk about the mass flow rate through the pipe, what I would say is that there's some effective velocity, which we call the bulk velocity, so UB times the cross-sectional area. So rho UBAC is equal to, in reality, it's equal to 0 to r, rho u of r, so that's all okay, times dA, where dA is 2 pi r dr. So this is our differential cross-sectional area. So this is essentially what I'm writing here now. We've divided through by, we're assuming rho is a constant, so we can divide through. And so when we substitute the u of r expression we have up here into this expression, we find out that the bulk velocity can be written as either 1/2 the maximum velocity, or they can be written as r squared over 8 mu minus dp dx. In a similar way, we can just insert the bulk velocity definition into the u of r model or u of r definition. Okay, and one of the important consequences, or one of the important ways of thinking about the velocity profile and one of its uses is in terms of the friction factor and the skin friction coefficient. So the friction factor, the Darcy friction factor, F, is really defined as a pressure gradient divided by the characteristic pressure gradient. So the pressure gradient in this case is nothing more than dp dx. So we're really looking at dp dx, and we're normalizing it by what we were saying is a characteristic pressure gradient. And we're ignoring the sign issues right now. So this is a pressure difference over a characteristic length scale. We're saying that characteristic length scale is the diameter, 2 times the radius. So you see that these both have the same units. These have units of pressure over length. And for the delta P in the characteristic value, what we're using is the dynamic pressure, 1/2 rho U bulk squared. So the friction factor is a very important parameter because it tells us what the pressure drops are in a pipe. And as long as we know certain parameters of it. So we can solve using dp dx as this ub over 8 mu r squared, and substituting that into our expression for the Darcy friction factor, basically just this expression here, we get the friction factor in terms of these parameters, ub and various radius and terms. But what's interesting about that is that for a laminar problem, And we're dealing with this laminar flow problem where the Reynolds number, again, for laminar cases is less than about 2300. This can be rearranged as 64 over the Reynolds number. So this is a really important understanding a model for flow in pipes. What this says is that if you know the Reynolds number, RED, then we know dP dx. And since dP dx is constant, it means we know delta P because it's just dP dx times the length. Okay, so the thing to do now is to talk about maybe an alternate representation for this, and that alternate representation is in terms of the skin friction coefficient. And so we talked about this from the pressure perspective, but it's just as easy to talk about it from the shear perspective. And so the shear stress on the wall, tau, on the wall is minus mu du dr at r is equal to r. We know what the velocity profile is, so we can simply take the derivative of it and evaluate it at r is equal to r, and we evaluate it as 4 mu ub over r. Make sure you see that this is really a very sort of simple recipe and description. Tau s looks like the viscosity times a velocity derivative with respect to r, gradient type term. And so we see the ub over r represents that du dr. So you always want to think about how to simplify terms, and it comes out explicitly that the units have to be all the same. The skin friction coefficient is defined in terms of the shear stress divided by this dynamic pressure term, 1/2 rho ub squared. If we simply substitute all the parameters that we've had in there, we find out that the skin friction coefficient is 16 over the Reynolds number and equivalent to the Darcy friction factor divided by 4.